Now that we understand what electrical current is, it's now time to talk about what is resistance. Because Georg Ohm realized whenever he applied a stronger voltage to a resistor, he would of course get more and more voltage. There was a direct relationship, meaning that if there's zero voltage, there's zero current. The stronger the potential difference he applied, the stronger the current would be. But whenever he used different materials would have different amounts of current going through. And he realized that certain materials had more resistance, other materials had less resistance. In this case, this one would have less resistance. This one had more resistance simply because there's more current when he applies a voltage. And he realized that this was simply a function of the slope itself. So the slope is equal to the resistance, or really R is equal to V divided by I. Okay, the potential difference divided by the current. Although in your reference table they'll say V is equal to IR, which is more common. V is potential difference, I is current, R is resistance, and the unit for R is going to be named after Georg Ohm. So it is the ohm, but we don't use that. We use the Greek letter omega. Okay, I'll draw that again. The Greek letter omega is the unit for resistance. But what exactly determines how much resistance there is? Well, let's take a look at what resistance really is and how that works. Okay, so what does this model really represent? You see, the ping pong balls are the electrons. And each of these points are the protons of the atom, meaning that the electrons have to push past, they have to squeeze past all those protons that are trying to hold on to those electrons because positive and negative charges attract. So in the end, certain materials grab on better than others.
And now the third factor,
take a look at it.
Resistance. This factor is controlled by the nature of the material through which the electrons flow. Again, going back to the motion of electrons in a metal, we said that they moved freely about and among the atoms. However, even in the best of conductors, some of the electrons collide with the atoms, tending to retard the movement of the electrons. This is the cause of electric resistance. Collisions are more probable in some metals than in others. Therefore,
okay. Which is again how we get the formula V equals to IR. Okay. Now, materials that follow that exact direct relationship we call ohmic resistors. However, materials that don't follow that trend, meaning that sometimes they curve, we call non-ohmic resistors. In this course, we're only going to be dealing with non-ohmic resistors, but be aware that not everything does follow the same course. In this next demonstration over here, we're going to take a look at how the different factors actually affect the level of current in a circuit. The most important thing to note is that when you increase the number of batteries in the circuit, you can see that the current over here is increasing. Okay? The question is, how much is it going to be increasing by? Well, that can be calculated simply based on the formula V is equal to I times R. So in this case, I would equal to V divided by R. So 9 divided by 550 is 16.4 milliamps. So if I decrease the voltage, of course, I'm decreasing the level of current. The most important thing to note, however, did the level of voltage, did the potential difference have any effect on the level of resistance? In other words, does the number of batteries affect the resistor? Well, obviously not, because they are two separate entities within the circuit. But it's important to write that down, okay? So the voltage and the resistance never affect each other. They only affect current. The more voltage there is, the stronger the potential difference, the more current there is. The more resistance there is, the less current there is, okay, and vice versa. If I decrease the resistance, I increase the current. So you can see that resistance and current are inversely related. Voltage and current are directly related, but voltage and resistance have no effect upon each other. Okay, so let's do a quick practice problem. A small flashlight bulb draws 300 milliamps of current. So I is equal to 300 milliamps, which is equal to 300 times 10 to the negative third amps. The potential difference is 1.5 volts. They ask us to draw the circuit. Okay. I'll label it as R, label this as V. What is the resistance of the bulb? R is equal to V divided by I, so it's equal to 1.5 volts divided by 300 times 10 to the negative third amps, which is really 0.3 amps, so it equals to 5 ohms. Now, the second part of the question, they ask, if you attach a weaker battery instead and we drop the voltage to 1.2 volts, how does the resistance change? And some of you guys might be tempted to take that resistance and do V over I again to solve for the new resistance. However, that'll be wrong, because the fact is voltage and resistance have no relationship with each other. It's still the same answer. Rather, what would change would be the level of current. I is equal to V divided by R. Now with 1.2 volts with the 5 ohms of current, you only end up with 0.24 amps. Okay? So keep in mind always, okay? Voltage and resistance never have any relationship with each other. So what has more resistance, a 50-watt light bulb or a 200-watt light bulb, when we think about this? Now remember, a light bulb, in terms of brightness, think about which light bulb is brighter, which is of course the 200-watt light bulb. Now, which one should have more resistance? Okay, keeping in mind that with a light bulb, when you have the filament inside, the electrons are all going through. They go through the filament, and basically you want there to be more current if you want the light bulb to be brighter, and you want there to be less current when the light bulb isn't as bright. Okay, so ultimately the resistance of the light bulb is very, very high, especially as compared to the wire itself. Skip that. So in this case, the 50-watt light bulb has more resistance because it's dimmer. And the second question is, do electrical wires have any resistance of their own? And the answer is very, very, very little. In fact, it's so little that if you were to happen to loop a wire or direct from one end of the battery to the other, well, let's take a look in this video to see what happens. By Survival Essential.
Today I'm going to show you how to start a fire with some steel wool right here. and a 9-volt battery and the steel wool. So I'm just
he
going to go
takes the
ahead and
steel wool,
clear the steel wool.
he pulls it apart.
And we'll burn it. And hard to put
Now
can.
take a
So
look.
it breaks down the fibers.
Ultimately,
Hold it.
after he puts the steel wool in and just tears it apart, he's eventually going to take the 9-volt battery and he actually manages to start a fire with that 9-volt battery. But how is he able to do that? Well, keep in mind that when the wire touches from one terminal to the next, the resistance is very low, which means that the current is amazingly high. It's so high, in fact, that when all those electrons are going through, they generate a lot of friction as they pass by the atom, and they generate a lot of heat. And that heat happens to be enough to melt the steel wool and to actually cause it to start a fire. Okay? Which is why if you were to actually have a short circuit within your household, okay? In this case over here, they have a picture of a short circuit. A short circuit is basically when you have an extra piece of wire that short circuits your battery. So instead of the current going from one point to the next and going through the light bulb, turning on the light bulb, the short circuit diverts all the current so it goes through that line instead. But wires have such low resistance that they generate a huge amount of current, a huge amount of heat. The short circuit inside the house will first of all turn off the light bulb. It turns off everything off. And then it would also, and it will also start a fire. Okay? So that's resistance.